So we've learned how to differentiate a bunch of different new functions. We have also looked at chain rule, probably the most important rule for differentiation, which allows us to differentiate anytime we've got a composition of functions that we know about. So if you have a function of a function, we can use chain rule to evaluate the derivative. But what if you've got a function multiplied by a function? Here's a few examples. What if we've got not e to the power of sine x, which would be a classic chain rule problem, but what about e to the x multiplied by sine x? So we can no longer think of this as a function of a function, but it's a function that we know how to differentiate multiplied by a different function, which we also know how to differentiate. And the question is, can we use our knowledge of those two separate derivatives to allow us to find the derivative of this combination? The last one in that list, x times ln x, is another where it's fairly obvious what we're doing. We have two separate functions that are being multiplied together, so we're going to use the product rule because it's the product of two functions. The one in the middle actually requires product rule because you've got 1 plus x to the 7 multiplied by 1 minus x to the 4, but it will also need chain rule along the way, because to differentiate 1 plus x to the power 7, you probably want to do it thinking of it as a function of 1 plus x rather than expanding it all out using binomial. And similarly, 1 minus x to the 4, you could expand it out and differentiate that way, but it'll be much easier to think of it as 4 lots of 1 minus x to the power of 3 multiplied by negative 1, the derivative of the stuff inside the bracket. So to get us started, see if you can quickly jot down, maybe make yourself a quick Venn diagram, see if you can work out which of these 6 functions you would need chain rule to differentiate, and which of them you would need product rule to differentiate, and which of them you would need both. Give it a quick go, and then continue the video when you're ready. All right, here's my Venn diagram. We've got a couple of things for each section, actually. Each of them will require at least one of these things. A and C are straightforward chain rule questions, because A is ln of sine x. The inner function is sine x, the outer function is ln of x. So we're putting sine x in as the input into the ln x function. So we'd have 1 over sine x multiplied by the derivative of sine x, which is cos. So you get cos x over sine x, which is actually the same as cot x. For C, we have y equals cos squared x. The notation for trig is always a bit annoying and slightly contradictory depending on what you're trying to do with trig. Cos to the power of minus 1 means something very different to cos to the power of 2. But in this case, cos squared x means cos x, all in a bracket, squared. So it's a cos x function inside of an x squared function. So we bring the power down in front, we reduce the power by 1. Instead of cos of x being squared, we've got 2 lots of cos of x, and then we multiply by the derivative of cos, which is negative sine. B and F are both product rule questions. B, we need to multiply e to the x by the stuff in the bracket. Now you could expand out the bracket first, and that would turn your e to the x multiplied by e to the x into e to the 2x, which would convert that piece into a chain rule problem. But you'd still have e to the x multiplied by x, and there's no getting around the fact that that one is going to have to be a product rule process. So you might as well do the whole thing by product rule. You would think of it as, I've got e to the x at the front as my first function, I've got e to the x at x as the second function. If I can find a way of combining the derivatives of those two to give me the derivative of the product, then that's what I'd be looking for. And for f, we've got ln x over x. It might look more like a fraction than a multiplication, but multiplication and division are basically the same thing. So this is ln x multiplied by 1 over x. And we're going to look in more detail when we get to quotient rule, how sometimes, depending on how complicated the function on the bottom of that fraction is, sometimes it can be very helpful to have a shortcut that will allow us to deal with that. Perhaps we know how to differentiate what's on the bottom of the fraction, but we don't know how to differentiate 1 over that thing directly. Well, as it turns out, chain rule is going to come in handy there as well, but we'll get to that when we do quotient rule. The last two, D and E, are a combination of the two. E is probably the most common sort that you'll see of these two. This one is a little like the 1 plus x to the 7 times 1 minus x to the 4 up above. It's a product of two functions, each of which has a little bit of mini chain rule going on inside. So sine 3x is something that you shouldn't need to stop and think about too much once you've had a bit of practice with chain rule. because you'll say sine of anything differentiates to cos of the same thing. So sine of 3x becomes cos of 3x. Oh, and then we just multiply by the derivative of 3x. So you get 3 cos 3x. So that's a simple one on its own to do with chain rule. And similarly with e to the minus x, it'll differentiate to minus e to the minus x. So you've got a little bit of chain rule to do in there, but it's still the product of two functions. E to the minus x is one of them, sine 3x is the other one. And with d, the other one, sine of x e to the x. Now there is a function inside another function, so you'd need to start with chain rule and say it's sine of something, so I'll turn it into cos of that same something, cos of x e to the x, but then you're going to need to multiply by the derivative of x e to the x. And to get the derivative of x e to the x, you will need product rule. So let's look at a rule we already have. If y equals f of x plus or minus g of x, then the derivative, dy by dx, will be the sum or the difference of the derivatives. So if you've got two functions added together, you can differentiate each one separately and add the results. And a very common starting point, a fairly logical conjecture would be, does that work with multiplying? Perhaps the same thing will happen when you have the product of functions. If the derivative of the sum is equal to the sum of the derivatives, maybe the derivative of the product is equal to the product of the derivatives. In other words, perhaps we just differentiate each of the two things and multiply them together, and that will be the same as the derivative of the two things multiplied. That's a reasonable thing to think at the beginning, but it doesn't take us very long to find a counterexample. Think about this one. We know what x squared differentiates to, but we can think of it as x times x, the product of two functions, each of which is just x. But x differentiates to 1, and the other x also differentiates to 1. So the product of the derivatives here is just 1 times 1, which is 1, not 2x, which we know should be the correct answer. There may be a little clue in there. The two bits we were looking at, x and x, somehow seem to be involved in the derivative of x squared, but they are not exactly the same as the derivative. We can't just differentiate each of those two things separately and multiply the results together. It's clearly not how it works. So how does it work? That's the question. Well, to make sense of it, we're going to start with just that example, x squared. We'll start with something straightforward and we'll build up to it. This picture represents x squared. In fact, the blue bit in the middle, that bit is x squared. So we have a width of x and we have a height of x, and that big square in the middle has an area of x squared. Now, the little extra margin that you can see, that corresponds to a small change in x. If we want to know how quickly x squared is growing, so as x increases by a small amount, how quickly does x squared grow, which is essentially the question, what is the derivative of x squared with respect to x? Then we need to think about a small change in x, which is often denoted with this delta symbol. Delta x represents a small change in x. So think of it as if x is 10, let's say, at this particular moment, maybe you're adding just 0.01 or something. So it gets slightly bigger. And also in the other direction. So if x is changing by some small amount, then it's changing by the same small amount in both directions. And here's where it gets interesting. We can look at the area of each of those strips. The width is x and the height is delta x for that strip at the top. So the area is x times delta x. And the strip on the right hand side is the same, x times delta x, because the height of the strip is x and the width is delta x. And hopefully you've noticed there is a tiny bit at the top that we've ignored, which has a width of delta x and a height of delta x. So the area is delta x squared. Now, the essence of a derivative is looking at a very, very small change and then imagining that very, very small change shrinking down until it's practically disappeared. And we look at what it's getting closer and closer to. So in this case, we can look at the size of the margin and say, what's the marginal increase? How much is x squared grown by when x grows by delta x? Well, we can see what it's grown by looking at those extra margins. So if we say that y equals x squared, then a small change in x squared, we're talking about a small change in y. So we might call that delta y. That's the change in the output. If we have y equals x squared, x is the input, y is the output. And we can see that the change in y, the small change in the output, which is x squared, that results when we change x by a small amount, delta x, that's just two lots of those thin strips plus that tiny square in the top right corner. So two lots of x delta x plus the delta x squared in the top right corner. Now this is where we start to look for a gradient, because what we care about is not the tiny change in x or the tiny change in y, but how big the tiny change in x and y are in comparison to each other. Specifically, how big is that change in y compared to the change in x? Well, we call the change in y delta y, we call the change in x delta x, and the ratio of those two is delta y divided by delta x. Well, if we just divide the left and right hand sides by delta x, that will give us delta y by delta x, delta y over delta x. We have 2x delta x divided by delta x. So that bit's going to cancel out. The delta x we had before, dividing by the delta x that we've got now, they're going to disappear. And then the next term was delta x squared. So a bit of that is going to cancel as well. And there we go. When you cancel those out, you find that we're left with something solid remaining. We've got 2x, because the delta x over delta x is just 1. But the delta x squared over delta x doesn't completely cancel. We've still got a delta x. Well, that's okay, because what's going to happen next is we're going to make delta x shrink all the way down towards 0. We're going to look at what happens as delta x gets closer and closer to 0. And the derivative, dy by dx, is defined to be the limit of delta y over delta x. So as we shrink those delta x, delta y terms to be smaller and smaller, delta y over delta x becomes dy by dx, and delta x, if it's on its own, it's going to disappear. Another way to think of this is we're looking at how the area of the blue box x squared changes, and the rate at which that box changes is based on the height and the width, or the thin strip at the top and the thin strip at the right hand side. And the width of those, or the width of the top one and the height of the one on the right, that's x. But the small change in x, that's going to shrink so small that those thin strips are essentially going to become like lines. So the rate of change of that two-dimensional shape is one-dimensional. Then the tiny piece in the corner is so small now. If you think about delta x becoming really tiny, like 1,000th or 1,000,000th, then delta x times delta x will be that much more tiny. So if delta x seems tiny compared to x, well, delta x squared will seem just as tiny compared to delta x. So when we compare it to x, it's so small, it essentially disappears. It becomes irrelevant when we're trying to make our square bigger. So there we have the derivative. This is what we're expecting, 2x. The derivative of x squared is 2x. But this is a really nice visual to see why it works. It's well worth spending time thinking carefully about this particular picture and making sense of where the x on the top and the x on the right hand side come from. If you want to make your square bigger, then you do it by adding a thin strip on the top of length x and a thin strip on the right of length x. Now it's essentially equivalent to you laying out a bunch of square tiles and you want to make the area of your square tile grid bigger. You're going to lay another line of tiles along the top and another line of tiles down the right hand side, and it will give you a larger area. Now you will have that sneaky extra tile in the corner, but if all you're laying is an infinitesimally thin strip along the top and an infinitesimally thin strip down the side, that tiny corner is so tiny you can't even see it. That's a good way to think about this. It gets weird when you start thinking about those tiny quantities, but differentiation takes that into account, sorts it out for us. Now we're just going to extend that idea. We're going to use exactly the same diagram, and we're going to see what happens if we have just any old function of x. It doesn't have to be x itself, it could be anything else. We're going to use the letters u and v to represent these, but think of it like this. U could be x squared and v could be sine x. So maybe we're trying to find the derivative of x squared sine x. So x squared multiplied by sine x, the product of the two functions x squared and sine x, perhaps. But so we don't get bogged down with the detail of those two, we're going to call them u and v, and we're going to represent them on a diagram as delta u and delta v. As x changes, u and v will change. And if you change x by a tiny amount, u and v will change by a correspondingly tiny amount, their own unique tiny amounts, depending on exactly what their functions are. So back to our diagram, this time we're going to imagine the width of the original box is u and the height is v, which gives an area of uv. Now that is our original function, the function I care about, the product of u and v. But then as x, which is sort of the independent variable behind the scenes that is driving these changes, if x changes by a small amount, delta x, then u will change by a small amount, delta u. And v will change by a small amount, delta v. And then we look at the area of those two very thin strips. The one at the top is the width u multiplied by the height delta v, and then on the right has a height of v multiplied by the width delta u. And in the top right corner again, we've got this tiny, tiny thing, the infinitesimal of an infinitesimal, this teeny tiny square, which is effectively so small that it's tiny compared to the tiny strips that we're talking about. We've drawn the whole thing exaggeratedly. You've got to try to imagine shrinking it down so much that the thin width of that strip becomes so thin you can't tell. And it's basically like drawing a thick line down the side. Now, if you do that, if you've got a line that's so thin you can hardly see the thickness of it, that all that counts is the length, then a single dot doesn't make any difference at all to the area. Well, let's look at what this ends up looking like in terms of algebra. A small change in uv, the overall function we care about, is equivalent to the size of that margin. So we have u times delta v, we have v times delta u, and we have that tiny square in the corner, or rectangle, whatever it might be, delta u multiplied by delta v. Then we compare all of those tiny changes to the original driving force, the tiny change in x. How much is this area, u times v, changing in relation to the variable behind the scenes, x? So delta uv, the small change in the product uv, compared to delta x, that's the thing that's going to turn into the derivative of uv with respect to x, when we eventually make these infinitesimals shrink down to nothing. And we get u times delta v over delta x, plus v times delta u over delta x, and finally a delta u times delta v over delta x. Doesn't really matter what order you put those things in at the end. There's two infinitesimal pieces, delta u and delta v, and you're dividing by one infinitesimal piece, delta x. Now, like we said, as we shrink these infinitesimals towards zero, the small change in uv and the small change in x, the ratio of those tends towards the derivative of uv with respect to x. And the rest becomes u dv by dx plus v du by dx plus, well, this is a little like a 0 divided by 0 that somehow turns into something sensible, which is the essence of differentiation, where you're looking at the gradient between a point and another point that is so close it's basically the same point. You effectively have 0 height compared to 0 horizontal distance, giving you a sensible looking gradient. But then we've got that multiplied by another of these infinitesimals, this extra delta u term, which complicates things. And in fact, in reality, it simplifies things, because whatever this derivative delta v over delta x is, well, that will turn into dv by dx for sure, but it's multiplied by delta u, which turns into 0. So that piece basically disappears. And we're left with, just like before, the only bit that's relevant for the rate of change of this area are the two tiny lengths that we've got on each end. The u delta v and the v delta u turn into u dv by dx and v du by dx when we're looking for the rate at which the area changes. So we could look at that piece and say that is essentially the product rule. That is how you differentiate a product. You need a combination of the function unchanged and the derivative of its partner, and the partner unchanged and the derivative of the original. So there are two different functions here. It might be x squared and sine x, and you care about the functions themselves and their derivatives. And if you've got all four of those things, each of the two functions and each of the two derivatives, you can combine them using this rule. Here's another way of writing it, which looks a little more messy, but it has the advantage of being accurate. So unlike what we were hoping for when we looked at what happens when you add functions, this tells us in reality what happens when you multiply functions. If you have y equals some function multiplied by some other function, the derivative will be given by the product of the derivative of the first with the second function plus the original function multiplied by the derivative of the second function. It's a little messy to say. It's easier to see it. It's a lot easier to use it and write it down. I'm going to show you a few different ways to say the same thing, but I would recommend you have this picture in your head whenever you're dealing with this, because it will help you to remember the formula and to help you to make sense of why the formula works. So we could say the first function multiplied by the derivative of the second added to the second function multiplied by the derivative of the first. It's got this nice symmetry in it, which reflects the symmetry of products anyway. UV is the same as VU, so whatever formula we're expecting to get, it should have been symmetrical because UV and VU are the same, so the derivative should be the same. This is the function version, f dashed of x multiplied by g of x plus f of x multiplied by g dashed of x. So you have each of the two variations where the first function is differentiated but the second one isn't, or the first function isn't differentiated but the second one is. Another way to write it is the way that we had down there. If y is equal to uv, then dy by dx will be u times dv by dx plus v times du by dx. Each function appears in its original form, u or v, along with the derivative of the partner function that goes with it. So u goes with dv by dx, v goes with du by dx. And here is probably the most efficient way of writing it. If we remember, we can use y dash to represent the derivative of y with respect to something implied. In this case, we can think of it as x. So dy by dx is equivalent to writing y dash. And then dv by dx and du by dx can similarly be thought of as u dash and v dash. So this one trips off the tongue a little bit more easily. Y dash equals u v dash plus u dash v. Or sometimes you say u v dash plus v u dash. Depends how you want to learn it. As long as you remember that each function will appear in its differentiated form in one of the terms and in its undifferentiated form in the other term, vice versa with the other one, you should be fine. So here's a quick example. We'll use our x squared and our sine x that we were talking about before. You'll notice the x squared appears in its undifferentiated form here, but then in the other term it appears in its differentiated form. And similarly, for sine appears undifferentiated here, and it appears differentiated here. We've got write one function down, multiply it by the derivative of the second, and then write the other function down, multiply it by the derivative of the first, and then those two terms that you've ended up with, add them together. You can even check for yourself that this works with simple things like x squared. We have x multiplied by the derivative of x plus the derivative of x multiplied by x. So x times 1 plus 1 times x, there's your 2x again. All right, let's try an example question. This one's a good one because it involves product rule and also chain rule. X plus 3 in a bracket squared is something you could deal with by expanding out the bracket. It's not difficult, but it's also nice and quick to deal with using chain rule once you get used to that. E to the 3x is another example of chain rule. It's a quick, simple chain rule because it's e to the power of something linear, so you're just going to have e to the power of the same thing multiplied by that nice single constant that you get when you differentiate something linear. The question asks us to find dy by dx, and in this particular case even helps you by suggesting you use product rule. You shouldn't expect that all the time. Usually you'll be expected to notice for yourself that product rule is required. So we write down our function, and then we identify the two separate pieces. Now you can do this like I did on the previous slide, just writing it out directly. But if you want a bit more structure, it's not a bad idea to write out u and v separately, so it's clear to you this is the two separate functions that are being multiplied, and then you can calculate u dash and v dash. This structure may feel like overkill to you for this sort of thing. That's fine. If you want to skip that, you'll probably cope just fine as long as the functions don't get too complicated. But we'll be coming back to this kind of notation when we deal with integration, because when you're trying to integrate the product of two functions, you end up using, in certain cases, you end up using a variation on the product rule. So sort of, if you integrate both sides of the product rule statement, then you end up with a statement that involves integration, and you can make use of that. In those cases, it's really helpful to have this structure. You'll be picking out u's and v's and du by the x's and dv by the x's, so you'll need to know which each one is. Once you've got all of those, you pick out the ones you need. So we'll take one from the top row, combine with suitable one from the bottom row. So for instance, if we take u, it's going to go with v dash, and when we take u dash, that's going to need to go with v. And as long as we multiply the appropriate things together and then add them, we will have our derivative. So we've got uv dash plus u dash v. We write it all out, and this is what we get. A couple of things to notice. If you have an exponential term in your product, then it will appear as a common factor after you differentiate. And that's because exponential terms always differentiate to themselves and then multiply by the derivative of whatever they had as their original power. But e to the 3x will differentiate to something involving e to the 3x. And therefore, even in its differentiated form, it's still going to have an e to the 3x in there. And in fact, our x plus 3 bracket has also given us something which is a common factor of both terms. Because it was x plus 3 to the power of something, even when that power comes down in front, we've still got x plus 3 to the power of 1. And that happens whenever you've got a bracket raised to a power, because that bracket will still be there. Chain rule sort of preserves the inside of that bracket. It'll just have a different power. So at this point, I've put this in bold because this will be a perfectly valid answer. If that's all it's asked you for, find u by the x, we're done. But it might be nice to combine things a little bit. We recognize that e to the 3x is a common factor of both of those separate terms, and also that x add 3 is a common factor. So if I pull out both of those, then the first term still has a 3 because of the 3e to the 3x, and it's also got an x add 3 because we used to have x add 3 in a bracket squared. The second term, the only thing left over when we pull out the e to the 3x and the x add 3, is that factor of 2. So we might finish up and give ourselves a final neater version that looks more like this. E to the 3x multiplied by x add 3 multiplied by 3x add 11. And even if you think you can do that in fewer steps, I'd recommend you set it out carefully and you include all the steps if you're going to simplify like that, because it's very easy to make little silly mistakes. They're obvious if you're writing out every step, but they are far from obvious if half the steps are in some vague, half-written form still in your head. Now, the next part of the question asks for the gradient of the curve at the point where x equals 2. Now, given that this curve has an exponential component to it, we're expecting a big answer. So 85e to the 6 shouldn't be hugely surprising for us. E to the power of 3x grows even faster than e to the x. And although we're only looking a little way along, x equals 2, well, that means we have an e to the power of 3 times 2 just for the height of the function. We already know that functions that are exponential have a gradient which is related to the same kind of function as the original. This one's got a quadratic multiplied by an exponential. It's going to be growing, it's going to be growing fast, and the gradient will be growing fast as well. All we have to do, as you can see, is substitute 2 in wherever we would normally see x. So instead of e to the 3x, we've got e to the 3 2's. Instead of x add 3, we've got 2 add 3, and instead of 3x's add 11, we've got 3 2's add 11. And we're done. Bit of a bonus section though, if you've got this far and you found u by the x, typical additional question here would be to ask you for stationary points. You might even be asked to analyze the nature of the stationary points, to look at the second derivative. And we'll get on to how you can deal with three things multiplied together in a moment. But let's look for stationary points first. Stationary points occur when the gradient dy by dx is 0. So let's look at when dy by dx is 0. Here's one of the factors. X add 3 is a factor. So we look at what happens when x add 3 is 0. And clearly we get a result, x equals minus 3. That would make dy by dx 0. But there's another factor. There's 3x add 11. So we can look at what happens when 3x add 11 is 0. We get x equals minus 11 thirds. So we found two different coordinates for stationary points. But dy by dx had three factors. It's also got that e to the 3x term. And although that doesn't give you any results, it's worth making a note in your solution of why you can safely ignore it. If you've got three things that multiply together to give 0, you know for sure that at least one of them has to be 0 for that to work. And if you go through each of the possibilities, then you'll exhaust all the different ways you can make the product 0. So e to the 3x being 0 would have been great. It would have given us another stationary point. But we know that e to the 3x is never equal to 0. And that's enough. You don't need to go into more detail than that. But we know enough about exponential functions to know that they are never going to equal 0. E to the power of anything. If it's a large number, we'll get a large answer. And if it's a small number, we'll get a small answer. If it's a massively negative number, well, that's just going to be equivalent to 1 over a massively large number. So we'll get answers very close to 0, but they never get to 0, and they never go negative. Incidentally, this is what the curve looks like. So it does do some weird things, and it obviously gets very steep and goes very high once we start getting into large positive values of x. But if x is low enough, we get to the point which is the minimum value for the quadratic. X add 3 in a bracket squared has its minimum when x equals minus 3. And you can see that even though e to the 3x might have otherwise been a very large number, if you multiply a large number, however large, by 0, you're going to get 0. So we've got that minimum point at negative 3, 0. But then there's also a maximum point, because the quadratic would like to start to rise again as the x values get large negative, because they're squaring a large negative number. But before they can get very far, the exponential decay takes over, and the dominant function in that partnership between the quadratic x add 3 squared and the exponential e to the 3x, the dominant function is always going to be the exponential. That's always going to beat any polynomial in a fight in the long run. There might be some blips along the way, might get a few punches in close to 0, but once things kick off, either to the left where we have exponential decay or to the right where we have exponential growth, the exponential is always going to win out in the long run. Now is a good time to have a go at some questions from exercise 9D. Any of those should be fair game. So we've done question 8 together. You should be able to tackle anything else from that exercise now. If you stick around, I've got one more little thing I'm going to show you. And that is what happens if you've got three functions. What if, for instance, on the last slide, we wanted to find the second derivative as well as the first? And at that point, we have e to the 3x multiplied by a couple of other brackets. Well, we can do a similar thing to what we did with chain rule. We can actually build up to it. There's no problem with repeatedly applying product rule. So try this. Find the derivative of x cubed, then use product rule to find the derivative of x cubed times sine x. And then given that you now know the derivative of that, find the derivative of x cubed sine x times ln x. Once you've tried that, come back and we'll see if we're on the same page. We're going to look for some common patterns. So x cubed differentiates to 3x squared. And then when we apply chain rule to x cubed sine x, we're going to have 3x squared multiplied by sine x. In other words, the derivative of x cubed goes with sine x unchanged. And then we add it to x cubed unchanged multiplied by the derivative of sine x. And then for the final bit, of course, product rule tells us that as long as we've got two things multiplied, we can calculate the derivative, assuming we know the derivative of the two things. Well, let's treat this as x cubed sine x multiplied by ln x. So this can be one of our functions, and this can be the other one. Once we think of it like that, we can see that the first function is something we already have the derivative of, and the second function is ln x. Now I've tried to keep the color coding here so you can see the light blue is the things that have been differentiated, and the dark blue are the things that have been left in their original form. And when we expand this out, we see even more clearly what's going on. We have 3 terms in the final expansion, because we had 2 terms in the derivative of x cubed sine x, and therefore we end up with 3 terms when you multiply that by ln x. And those 3 terms have got a 3x squared that's been differentiated, and then a sine x and an ln x that haven't. And then we've got, in the second term, cos x that's been differentiated, and an x cubed and an ln x that haven't. And finally, we've got the 1 over x, that's the derivative of ln x, multiplied by an x cubed and a sine x still in their original form. And that general pattern that you see, where you've got the 3 original functions put in all the different combinations where one of them has been differentiated and the other 2 haven't, that pattern works in general. In fact, this is a more algebraic and general abstract way of showing the same thing. UVW can be thought of as being U times VW. So product rule tells us if you want the derivative of UVW, you need the derivative of U multiplied by VW unchanged plus U unchanged multiplied by the derivative of VW. But then the derivative of VW itself can be broken apart. That's what these brackets are on the right. You can break that apart using product rule once more. V dash W plus VW dash. And once you see that, we can recognize this general pattern. Each of the terms appears. So in every one of those 3 terms, you've got each of the 3 original functions appearing. But in each case, one of them is differentiated and the other 2 are not. So that's quite nice. And you can probably see now how that would extend nicely to 4 things multiplied or even more. Can get a bit tedious, but it's certainly possible. So if you want a bit of a shortcut to just applying product rule repeatedly, then you can use this. However, don't panic if that looks like too much to try to take on board and make sense of. There's no expectation that you memorize this, but it's a really useful one to understand why it works and how you can extend. Because if you do end up having 3 things to multiply, or 3 things multiplied that you need to differentiate, then it's nice to know that you can apply product rule to any product within those functions. And then if a part of that is itself a product, you can apply product rule again. You can apply product rule and chain rule repeatedly within one another whenever you need to. So try to look at the main problem as, well, what am I looking at right now? Is it an outer function with some stuff inside, in which case start with chain rule and see what's left inside? Or is it 2 things multiplied, in which case start with product rule and see if you can deal separately with the separate bits that are multiplied. More than 2 things multiplied, treat it as if it's just 2 things, just like we did here. We've got clearly 3 different functions, each of which on their own we can differentiate, but we can break it apart and say, let's treat it as ln x times some other nasty stuff. And product rule will help you deal with the nasty stuff as and when you get to it.